Let's see, any questions this morning yet? I'm still, I've got lots of crud going on this week, but still trying to get this stuff prepared for a lab handout for this week, and it looks like it may not happen until tomorrow morning is when I'll have enough time to devote to that. But it'll be it's just a worksheet to fill out, so I'll give you a week for it. And then next week's is going to be another worksheet, and those will be things that we can actually work through much of next week's lab during a 2-hour lab period on Tuesday, if we do that. So that's a possibility anyway. And today we're going to be looking at the motion of charged particles in electric fields. And I put an announcement up last night with a link to a PDF file that I can't remember which textbook I copied it out of now. And it's not in the heading or the footing on the pages. So I don't know where I got that stuff. It might have been, well, I'm not sure actually which one it came out of, but at any rate, it does quite a few example problems in there. So turns out if you have a uniform electric field, the acceleration of the particles, charged particles in there, will be constant. And so we can use constant acceleration equations to deal with those. I was going to check real quick before I do anything else.
Mr. Ham, have you posted the formula sheet for this quarter?
Oh, maybe not. Yeah, so use the book for the next few hours and I'll try to get that posted up there soon.
Okay, thank you.
Yeah. Oh, I'm using a different microphone today. It's one that I used most of the time last quarter, and I'm wondering, apparently you can hear me, Riley?
Yeah, pretty clear.
Okay. That one wasn't working for a while, and I had gotten it turned around in its holder, and the reason it wasn't working was because it's got a sensitivity knob on it, and somehow in turning it around, I'd turned the knob all the way down, which makes a microphone not work. So I think I figured that out last night. Hopefully it's not too loud. It's sitting right in front of where I sit to solve problems. So I hope it's not too loud when I'm working there, but you should have volume control knobs on your computer just in case. All right, I'll switch back to that thing and we can do some problems of this nature. One thing I wanted to do was just start off with a general introduction to this topic. If you have an electric field given by E, that is force per unit charge, newtons per coulomb, and the actual force on the charge acting will be whatever the value of the charge is for the particle times that electric field. And Newton's second law is still going to work just fine. And so we can say that that will equal MA. If we've got an electric field acting, it will almost always be the force on the charged particle due to the electric field will almost always be way stronger than the gravitational force. Although I think one of your homework problems has to do with a situation where they're balanced, but that wouldn't be too bad. But most of the problems we'll look at, this force is going to be so much larger than mg that we can ignore mg in the problems. And you'll see accelerations that show up in these things, and they're generally quite a bit bigger than 9.8 meters per second squared. So the acceleration then ends up being QE over M, and that's something that's not hard to calculate. And usually, well, this section is titled The Acceleration or the Motion of Charged Particles in Uniform Electric Fields. So if they're uniform, that means the acceleration is going to be uniform and constant. One of the problems we'll do today, maybe, yeah, I think one of the ones today has to do with a charged particle at first in a region where there is no electric field, and then it enters a region of a uniform electric field. And this is actually possible. There was a, let's see, used to be electronic devices called tubes, and you may have heard of a tube amp before, amplifier, something like that. And what you might have in those things is a couple of metal plates, and the spacing on these isn't particularly accurate or anything, but it's just kind of a situation of what you have. And what you would have is maybe a positive charge on the top of this plate, and then a negative charge on the bottom of this plate, and those would be equal and opposite charge distributions. And then you can drill a small hole through the bottom plate. And outside of the region between the plates, you'd have the electric field equaling 0. And inside the electric plates, or between the two plates, you'd have an electric field in there that would be uniform. And if you shot charged particles through this little hole, which is doable, they'd go from a place where the electric field is 0 to a place where you have a uniform electric field virtually instantly. And so there'd have to be some place where the field goes from being 0 to whatever it is in between these plates. But it's not hard to give charged particles fast velocities like, say, 10 to the 6th meters per second. And so they can spend very little time in that kind of transition region. And so you can think of them as just going from 0 electric field to an electric field in a very short period of time that you ignore. So that's what we'll be doing in these problems. So hopefully going from here to here isn't too hard for you. And that's what we'll be doing today. Numbers that we'll be using quite a few times today are, let's see, the mass of an electron and the charge on an electron. So mass is equal to 9.11 times 10 to the minus 31 kilograms. And the charge, actually for the charge Q, we use that E, and it's actually minus E in this case. And so it'd be minus 1.60, and I'm going to add another significant figure on this today, times 10 to the minus 19th coulombs. And then for a proton, and I don't know if we have any problems with anything other than electrons or protons. Let's see. Electron, electron, protons. Okay, yeah, for a proton, the mass is 1.67 times 10 to the minus 27th. Whoops, lost it. Anyway, kilograms. And then the charge is equal to plus E. So it's the same charge as the electron, but positive. So those are a couple of numbers that we'll be using today. All right, we have an electron placed at rest in a uniform electric field of 520 newtons per coulomb, then released. Later, the experiment is repeated with a proton. Calculate the speed of each particle 48 microseconds after being released. One of these may not correspond to reality. Actually, the whole thing may not correspond to reality. Just how do you place an electron at rest in a uniform electric field? One way to do it might be to shoot an electron into the field so that the electric field slows the electron down and stops it, and then it'll be at rest for an instant. And we could imagine what will be the speed of it 48 microseconds later. And we can do this with both of them. So let's see how this works out. We're going to be using equations of constant acceleration. So if you remember what those were, you had things like x is equal to x naught plus v naught xt plus 1/2 at squared, or v equals v naught plus at, or we got lots of things, but let's see, v naught x times t and plus a sub x times t. We may actually have some projectile motion. In fact, I think the third problem we do is a projectile motion problem. So we'll be pulling in old knowledge on these things. All right, but we've got an electron in this case, and we know the strength of the electric field. We don't really care about the direction of the electric field in this case. It's just that the electron is initially at rest, and the electric field will act on it. For an electron, the acceleration is going to be QE, but the electron has a negative charge. So the electron will be in the direction opposite the electric field. Did I say the acceleration will be in the direction opposite the electric field? I'm not sure what I just said, but at any rate, let's see what we'll have here. Acceleration is just going to be QE over M. And so I'm just interested in the magnitude here. So I'll go with the magnitude of the charge, 1.60. I've only got 2 sig figs on that thing and 2 on that. So I'll just use the 1.60 times 10 to the minus 19th coulombs times 520 newtons per coulomb. And you think, oh, okay, it doesn't have much charge, so it won't have much acceleration, except that mass that goes down there on the bottom, 9.11 times 10 to the minus 31 kilograms. You'll end up with the coulombs dividing out, you'll have newtons, which is a kilogram meter per second squared. And when you divide that by a kilogram, you get an acceleration of meters per second squared. And I think it's going to be kind of big, because 10 to the minus 19th divided by 10 to the minus 31 is 10 to the 12th. So that'll dwarf everything else going on in here. Whoops. Scientific notation. Yeah, we get an acceleration of 9.1 times 10 to the 13th meters per second squared. This isn't an unusual acceleration for an electron in a charged particle. In fact, this isn't a particularly strong electric field. You could make an electric field that strong, let's see, trying to think, if you had a 9-volt battery, let's see. Yeah, if you had a 9-volt battery and you put two metal plates 1.7 centimeters apart, you'd have an electric field that strong. So wouldn't be too hard. I did some math that's beyond the scope of the course so far. It will be doing that the week after next. But anyway, it wouldn't be too hard to do. All right, that's a big acceleration. How fast will it be going 48 microseconds after being released? Well, how fast? We'll use our V equation. V is going to equal V naught x plus AT, but V naught is 0 because it starts from rest. So it's just going to be AT. And so we'll have 9.1 times 10 to the 13th meters per second squared times 48 microseconds. That's 48 times 10 to the minus 6th seconds. So let's see what we get here. Great. Let's see, 4.4 times 10 to the 9th meters per second. Any problems? Anyone notice anything about that number?
Wouldn't it be greater than the speed of light?
Yep, that's the problem. And we'll find out at the end of the quarter when we study special relativity that the electron starts behaving differently when you start accelerating it close to the speed of light. And we'll find out that, for one thing, it would take an infinite amount of energy to accelerate it to the speed of light. So you're not going to have an electric field quite like this one. We could try to figure out how could you possibly accelerate it for that long, because if it's going that fast, it's going to go quite a ways in 48 microseconds. And we could figure out just how far it would travel if it had that acceleration for that long. And the x would just equal 1/2 AT squared. So 1/2 times those 9.1 times 10 to the 13th meters per second squared times the 48 times 10 to the minus 6 seconds squared. This may not be a completely unreasonable distance, but we'll see. Okay, I get about 1.0, actually, 1.0 times 10 to the 5th meters, which is, let's see, that would be 100 kilometers, where you'd have to have this uniform electric field, or about 62 miles. That could be kind of challenging to have a place that big with a uniform electric field in it. So it might be hard to build this thing in the first place. And this wouldn't work. This is basically depending on, or the acceleration equaling QE over m is depending on Newton's second law, and things start to change after you accelerate particles to close to the speed of light. Their inertia seems to increase, and instead of just having the mass down there, you have the mass multiplied something that ends up being speed dependent, and so it gets more complicated, and we'll learn how to deal with some of that. I'm not positive spring quarter that, or at the end of the quarter, that we could even address this problem, but maybe we could. We could imagine having a uniform electric field this long, and actually that's a way we could do it. If we knew that it was being accelerated over a distance this great, we could calculate what its speed would be, but we'd do it, since it won't have uniform acceleration, we'd have to do it with an energy calculation, and we'll be able to do that. So it'll be kind of a fun problem, actually. All right, well, let's do the same thing for the proton. And actually, all I'm going to do is just go V equals QE over M times T, V equals AT. So I'm just going to redo this calculation with the proton mass in there instead, and I'll have 1.60 times 10 to the minus 19th coulombs times 520 newtons per coulomb times 48 microseconds. But I have to divide by the mass of the proton, 1.67 times 10 to the minus 27th kilograms. And so for the proton, we're not going to be going so fast. Okay, this one is, the proton's only going to be going about 2.4 times 10 to the 6th meters per second, which is a bit less than 1% of the speed of light, which is 3 times 10 to the 8th meters per second. So at less than 1% of the speed of light to two significant figures, you probably wouldn't notice the relativistic effects. They don't show up until, oh, let's see, they don't get bigger than 1% until you, I think you're around 5% of the speed of light. I don't remember exactly. I'd have to do a calculation, but at any rate, it's not gonna matter here. But that's the way you would do this problem if you were ignoring special relativity. So if you had a weaker electric field, or if you considered a much shorter time interval, you could do this fine without having to worry about special relativity. All righty, here's another one. An electron traveling with an initial velocity of this, 8.6 times 10 to the 5th meters per second, enters a uniform of, or a region of a uniform electric field given by that. And so, let's see, the initial velocity is in the I-hat direction. That's V naught. And it's a vector. The electric field points in the positive I-hat direction, but remember the acceleration of the electron is going to be Q times E, and because it has a negative charge, the acceleration will be in the negative I-hat direction. So it starts going that way, but the acceleration is that way, which means it's slowing down. And we can do this all one-dimensionally now. If we just think the electric field is that way, the acceleration is this way, V naught is that way, and we'll just call positive that way. So positive is to the right, and I can just write down the equation V equals V naught minus AT, and the magnitude of the acceleration is that. The magnitude of the acceleration will be negative. So if I just deal with magnitudes of this thing, we should be fine. And we're interested in when this is 0. So AT will equal, V naught at that point, or the time it'll take to stop is going to be V naught over A. And we can do various things. Second question asks the time it takes for the electron to come to rest after it enters the field. So we can do this stuff. The acceleration, magnitude-wise, 1.60 times 10 to the minus 19th coulombs. And the electric field here is quite a bit stronger than the other one. 4.1 times 10 to the third newtons per coulomb. Actually, it's roughly 8 times stronger than that other one. And then divided by mass of the electron, 9.11 times 10 to the minus 31 kilograms. It'll still be a big acceleration compared to what we're used to. Still get a larger acceleration than the other one. What's going on? Did I put a number in wrong? 1.6 times 10 to the minus 19th. That one was just 520. Oh, I'm getting a bigger acceleration because we have a stronger electric field. Never mind. I get about 7.2 times 10 to the 14th meters per second squared to the left is the direction of that. Okay, so for the time for it to come to a stop, this was part A. Part B, the time is just going to be that initial velocity divided by the acceleration. So 8.6 times 10 to the 5th meters per second divided by 7.2 times 10 to the 14th meters per second squared. And if you look at the units, meters per second divided by meters per second squared, flip the bottom and multiply, you'll end up with seconds. And Well, I must have put something in. Oh. Don't know where that came from. Oh, I was continuing a previous calculation. So I get about 1.2 times 10 to the minus 9th seconds. So 1.2 nanoseconds. This is kind of like stopping on a dime. I think that's such a tremendous acceleration. If it was a macroscopic body, something that was made up of cells and stuff like that, undergoing an acceleration like this, it would basically squash into a really thin puddle. So we'd have that. Okay, and then the last part, how far does it move in the electric field before coming to rest? I could use this equation if I didn't want to use the time. Time-wise, I could use this equation. I could use x minus x naught is equal to v naught t minus 1/2 at squared and plug it in that way. Or, that's one equation. I could use, let's see, I can use v squared equals v naught squared minus 2a delta x, or maybe it's plus 2a delta x, I don't remember. We do have a negative acceleration in this case. So since this side is going to be 0, probably minus in this case, because I do have a negative acceleration. Solve that over there. Delta x is going to equal v naught squared over 2a. And I'd rather do it this way because then I don't have to plug in such a complicated equation. So not bad. Anyway, v naught was 8.6 times 10 to the 5th meters per second. And that gets squared, and then 2 times that acceleration. And on top, I'll have meters squared per second squared. On the bottom, just plain old meters per second squared. So I'll end up with meters. That's good. And I get about 5.1 times 10 to the minus 4th meters, which is half a millimeter. And so I think I used the term stop on a dime. Actually, this would stop on a lot less than a dime. At the distance much smaller than the thickness of a dime, or quite a bit smaller than the thickness of a dime anyway. So pretty quick. Okay, any questions on that one? We're using old equations and applying them to a new situation, but still there's not a whole lot that's different from things that we might have done fall quarter. In fact, I think I did give you an electron problem fall quarter, or we did one as an example problem. Okay, this one's, I don't know how well you can see this illustration here, but we have protons projected with an initial speed of 9.55 times 10 to the 3rd meters per second, which isn't very fast for a proton. And they're projected into a region where a uniform electric field given by that is present. as shown in the figure below. So the idea is they're launched in here. There's some little tiny hole here that they're launched through. And so they've got an initial velocity there that makes some angle with the horizontal. And in this case, the electric field points down. Protons have a positive charge, so the force on them and their acceleration will then be in the direction of the electric field, which is down. So this is a projectile motion problem, but it's got a different acceleration than that due to gravity. And we'll calculate that first just to see what's going to happen here. The point is to hit a target that's 1.27 millimeters away from where the proton entered there. And I think just to keep this problem interesting, I'm going to rewrite that electric field as minus 7.20 times 10 to the second newtons per coulomb in the j hat direction. So we'll have three significant figures all around. And not that it matters a whole lot, but we'll be able to get the angle theta more precisely, or at least to the nearest tenth of a degree that way. And the total time of flight for each trajectory. Well, let's review our equations for projectile motion. Things that we had in that case is that V naught x is equal to V naught cosine theta. Let's see, V naught y is equal to V naught sine theta, and we don't know theta yet. That's what we're trying to figure out, so we won't know that very well. V naught x is equal to a constant though, because there's no acceleration in that direction. And well, V naught x is a constant anyway, but I shouldn't say that. I'll say that V sub x is going to be constant, and it will equal that V naught cosine theta. V sub y, though, is going to equal V naught y minus AT, where A is going to be the magnitude of the acceleration. When we did projectile motion problems before, it was always V naught y minus GT, but not this time. We'll have a different acceleration. And we'll probably find out that it's safe to ignore the acceleration due to gravity. Technically, if this is actually a horizontal surface, you could also have a plus g times t in here, but I don't think it's going to make any difference in this case. We'll find out soon at any rate. So those are those equations, but then we've also got that y is going to equal y naught, which we can call 0, plus v naught y t minus 1/2 at squared. And so the way we solved these was to figure out what the time of flight was. We'd set y equal to 0. We can define y not to be 0 and solve this equation for when the thing comes back down, and that would give us t. And then we would plug that into the x equation. X is just going to equal v naught xt. So we can figure out how far it goes. Other things. On this, I'm going to let x naught equals 0 and y naught equals 0. Just define this point where the proton comes out of there to be the origin of our coordinate system. Now, there was another formula we could get, and it was for the range of a projectile. And what we did was solved let's see, one of these equations for T and plug it into the X equation, if I remember right. Anybody remember how to get the range of the projectile? I think if you let V sub y equals the negative of V naught y. Yeah, the time of flight when you begin and end at the same position. Ends up equaling, you'd have V sub y equals the negative of V naught y. There's that symmetry to the stuff. That'll be V naught y minus AT. And that means the time of flight will end up being 2 V naught y. I'm doing a few algebra steps at once here, divided by A. Bring that across, 2 V naught y. Yep, that's the time of flight. And then if I take that and drop it into the X equation, which is just V naught X times T, you'd get the distance that the thing travels. So the range will end up equaling V naught X T, but when I plug in the time of flight there, I'll get 2 V naught X V naught Y divided by the acceleration. And then I use that fact that V naught X is equal to V naught cos theta, V naught Y is V naught sine theta. So I'll have 2 V naught cos theta, V naught sine theta divided by A. And the range will equal V naught squared times 2 cos theta sine theta divided by A. And the only double angle formula I can remember is that the sine of 2 theta is equal to 2 cosine theta sine theta. So this ends up being V naught squared, sorry if I'm writing too small to be seen, sine of, 2 theta divided by A. And that's the range of the projectile. So I'm going to get a fresh sheet of paper up here so we can finish off this problem. We happen to know the range. We know that the range is 1.27 millimeters. You want to hit this target over here. X marks the spot there. And so that's what we're after. So we should be able to figure that out, although we have to calculate the acceleration first. So let's do that. The acceleration of this is going to be, ooh, that's got the angle built into it also, doesn't it? No, it doesn't. The acceleration is just going to be, well, the force on it is going to be the charge on the electron, or the proton, excuse me, times E, whoops. And if I'm just after the magnitude of the acceleration, I know it's going to be downward. It's just going to be 1.60 times 10 to the minus 19th coulombs times the value of that electric field, which is 7.20 times 10 squared newtons per coulomb. And I can get that, but the acceleration is in magnitude will be E over m. So I'll take that product, 1.60 times 10 to the minus 19th coulombs times 7.20 times 10 squared newtons per coulomb and divide by the mass of the proton. 1.67 times 10 to the minus 27th kilograms. Now this thing is just about 1, and so we'll get 10 to the minus 19th divided by 10 to the minus 27th is 10 to the 8th. And I'll have an acceleration that's roughly 7.20 times 10 to the 10th. So I can safely ignore the acceleration due to gravity. Oops. Divided by. Yeah, I get about 6.90 times 10 to the 10th. Meters per second squared. So if I was actually taking account of everything on this equation here, I would have this number plus 9.8, and the 9.8 is not going to show up until you get about 8 or 9 decimal places to the right on this, so it's not going to make any difference. Anyway, there's the acceleration of our particle, and now we know our range. I'll use an R for range. That will equal V naught squared sine of 2 theta divided by A. And I know that, I know A, and I know V naught, so I can figure out what theta happens to be from that. So let's do that. Sine of 2 theta will equal AR divided by V naught squared, which is 6.90 times 10 to the 10th meters per second squared. Here's hoping we come up with a number less than 1 for this thing. Times R, 1.27 times 10 to the minus 3rd meters. That'll be meters squared per second squared. Unit-wise, we're going to be good. The initial velocity is 9.55 times 10 to the 3rd meters per second. And we have to square that. So sine of 2 theta is equal to let's see, got that. I get 0.961 for that sine of 2 theta there. Now, we're supposed to get 2 angles out of this somehow. And to understand how that works, I'm going to make a quick sketch of the sine function. And so this would be pi over 2. I've got a value of 0.96, and so here's my value of the sine function that I get here, and there are actually 2 possible angles where that could work, and we need to figure out how that can work from there. One of the values of 2 theta is going to be a little bit to the left of 90 degrees, and my calculator's in degrees mode, so maybe I'll just call this 90 degrees. The other one is going to be the same distance to the right of 90 degrees. Or you can think that that's one of the values of 2 theta. One of the values of theta, when you divide by 2, will be a certain distance to the left of 45 degrees. The other one will be just as far to the right of 45 degrees. So with my calculator, I'd get that 2 theta is equal to, I'll just do the inverse sine function of that last number. I get 73.9 degrees, which happens to equal 90 degrees minus 16.1 degrees. I could have done that in my head, for Pete's sake. The other one will be 90 degrees plus 16.1 degrees. Okay, now this is something your calculator can't tell you. I have to do a sketch to figure things like this out. And so that would be 106.1 degrees. And let's see, half of that would be basically 53.1 degrees. So with one of them, I get theta is 53.1 degrees. With the other, I get theta is equal to, let's see, that's 36.9 degrees about, or maybe 37.0. So anyway, those are the 2 angles that I get that would produce that. Now, what about the total time of flight for each trajectory? Somewhere here, I'd had the time of flight. Oh, it's 2v0y over a is what the time of flight happens to be. So we can figure that out. v0y is equal to v0 sine theta. And so the 2 values for the time of flight, or the v0y, I can just plug into here. And let's see, what was v0 again? 9.55 times 10 to the third. With one of them, I get 5.75 times 10 to the third meters per second, and that's for theta equaling 37.0 degrees. And for the other one, I would get 7.64 times 10 to the third meters per second. And that's for theta equaling 53.1 degrees. Okay, so let's see. I'll use the back of that one. The time of flight then is just equal to, you get that one by using more paper. This equation, that v sub y, which is v0 y minus at is equal to minus V naught y when it comes back to when it hits the surface. And so you get that 2 V naught y equals AT, or the time of flight is 2 V naught y over A. So we can just do this for one of these, and it's a repetitious calculation. But for the 37-degree angle, it'd be 2 times 5.75 times 10 to the third meters per second divided by that acceleration, which somewhere I've got it here. There it is. 6.90 times 10 to the 10th meters per second squared. So for the 37-degree angle, the time of flight is 2 times. Oh, that's a 10. Couldn't read my writing. I get about 1.67 times 10 to the minus 7th seconds, which you could actually write as 167 nanoseconds. So not very long at any rate. And then for the other one, it would be a slightly longer time of flight because it's got a slightly larger V naught y. And this is 437.0 degrees. All righty. Well, that last one was a relatively complicated problem. And we had to pull in stuff that we haven't used since way back fall quarter. There was a experiment I did as a student at Eastern, and let's see, trying to think if this was also a way of getting the charge to mass ratio. We've got a setup for it. In fact, late in the quarter, we might do this as an experiment. It has to do more with magnetism than electric fields, but first we accelerate electrons in an electric field, and then we bring them into a region of a uniform magnetic field. And turns out that in a uniform magnetic field, charged particles will travel in a circle, and if their orientation is right. If it isn't right, they'll travel in a helix. And by measuring the radius of the circle and knowing how fast you got those electrons going, and you know that how fast that is because you know the strength of the electric field through which you accelerated them. So knowing that, you can figure out the charge to mass ratio of the electron. And that's an experiment I've only got one setup for. So late spring quarter, or late this quarter, like probably sometime in May, I'll have you sign up for times to come out to school as duos maybe, and you can go through the data gathering for that thing, and we can see what we can come up with for the charge to mass ratio of the electron. Okay, that's about all I can think of for today for the charged particles. We're going to skip the electric dipole stuff. The idea of a dipole is that you have a positive charge and a negative charge that are separated by some distance d, and they're maybe sort of locked together in that configuration. And there's something that you call the dipole moment, which is the charge, magnitude of the charge on either one of them times their separation. And many molecules have dipole moments, even though they're a more complicated configuration than this. For instance, the water molecule, the electrons from the hydrogen atoms spend most of their time with the oxygen atom, and that sort of generates a dipole moment to that one. You've got the oxygen here and then the two hydrogens, and the hydrogens basically donate their electrons to the oxygen atom. And so it's as if this thing has a net negative charge and these two have a net positive charge, this end of the molecule. And so this acts like a dipole. And it's that nature of the water molecule that lets you do all kinds of neat stuff. In fact, there's a demonstration I usually do the first day of this class that shows that behavior. But anyway, we're going to probably not study the dipole stuff, although I'm tempted to bring it up on Monday just for a little bit anyway. Okay. I'm hoping by sometime tomorrow I'll be able to get that stuff posted for the Resistivity Lab. And again, it's a worksheet that you'll fill out. It's actually an experiment that I've had the Physics 110 class do before. And so I took the measurements, but this is the first time I've ever done it with the very sensitive ohm meter that I have at school. And so we'll be doing with that. But let's see, stop that share. Any questions pop up during this? Let's see. Oh, yesterday I got busy working on a project and I forgot to post the lecture from yesterday. And in fact, I forgot to post the lecture from Tuesday too. So I'll have to upload that to YouTube if I haven't already done so. And then we'll be caught up on those things and I'll get going on that. So if there aren't any other questions, I'll keep an eye on my message thing if any questions do pop up, but we'll stop here.